Picture this scenario. You're driving down the highway, the windows are down, and the wind is just rushing in. You realize you're going to be late for dinner, so you shout at your dashboard, text mom, I'll be there in 20 minutes. You wait, the little loading circle spins, and then after a solid 3 seconds of contemplation, your car's voice assistant cheerfully replies, playing Money by Pink Floyd.
Oh, every single time. Or, honestly, even worse, it just gives you that sad little, I didn't quite catch that beep.
Exactly. And it is infuriating because you know that underneath that dashboard is absolute state-of-the-art technology. I mean, billions of dollars of R&D, massive server farms, the works, and yet a little bit of wind noise or a slightly mumbled word and the whole thing just falls apart.
Right, it's the classic brittleness problem.
Yeah.
And honestly, it has been the dirty secret of speech recognition for a decade. In a quiet lab, these models are perfect. In the real world, they shatter like glass.
Well, that gap between the pristine lab and the noisy highway is exactly what we are unpacking today. We have a stack of research here for our deep dive, centered around a really landmark paper from OpenAI. The title is a bit of a mouthful. It's called Robust Speech Recognition via Large-Scale Weak Supervision. But the real star of the show is the model they built, which they call Whisper.
Yeah, this paper is fascinating because it marks a massive philosophical shift in AI. For years, the industry was obsessed with specialized precision. OpenAI looked at that and basically said, no, we don't want a specialist that needs a quiet room. We want a generalist. We want something that works everywhere, from a library to a noisy construction site.
So our mission today is to figure out exactly how they pulled that off. We are going to look at the architecture, which is surprisingly simple, and this concept of weak supervision, which sounds like a criticism, but actually turns out to be the secret sauce. And we definitely need to talk about the data, because the numbers here are frankly absurd.
They really are. It is a data story just as much as it is a model story.
But before we get to their solution, let's dig a bit deeper into the problem. You mentioned brittleness. Why were the old models so bad at handling background noise?
So if you think about how we traditionally train AI, we use what are called gold standard datasets. In the speech world, the really famous one is LibriSpeech. It's about 1,000 hours of people reading audiobooks.
Okay, so high quality, clear enunciation, professional microphones, and absolutely zero background noise.
Exactly. And researchers would compete to get the best possible score on LibriSpeech. They would tweak their models to get 99.9% accuracy on that specific data. But the paper points out that this is, well, it's like a student who memorizes the answers to the practice test.
Right. They know that question 5 is C, but they don't know why.
Precisely. There was a famous study in computer vision that the Whisper paper actually cites to explain this. A model became superhuman at identifying objects in a data set called ImageNet. It was statistically better than a human at saying, that is a cat. But when they showed it the exact same objects from a different angle or with different lighting using a dataset called ObjectNet, the performance just dropped by 40%.
So it didn't actually learn what a cat was. It learned what a cat photo in the training set looked like.
Right. It learned spurious patterns. Maybe it learned that if the background is blurry and green, the object is a cat. That is a dataset quirk, not a feature of a cat. And the exact same thing happens with audio. If you train on audiobooks, the model might learn that a sentence always ends with a specific cadence, or that silence always means a pause between sentences. But in a pub or a car, there is no silence. People don't talk like they are reading a book.
So the model hears a car horn and thinks, I've never heard this phone before, and just panics.
Exactly. And the traditional fix, and correct me if I'm wrong here, but you've probably seen this in the tech news, the fix was fine-tuning.
Right. That's where they take the audiobook model and sort of retrain it on car noise, right?
Yeah, that has been the standard workflow. You build a base model using something like Wave2Vec 2.0, which is the previous state-of-the-art, and then you fine-tune it. You want it to work in a hospital. Yeah. You fine-tune on medical dictation. You want it to work for legal transcription. You fine-tune on court records.
Which sounds incredibly expensive and exhausting. I mean, you're basically playing whack-a-mole with environments.
It's totally endless. And it is dangerous because every time you fine-tune for one specific thing, you tend to break it for everything else. It's a phenomenon called catastrophic forgetting. If you teach the model medical terms, it might completely forget how to understand street slang. The OpenAI team wanted to get off that hamster wheel. They wanted zero-shot performance.
Zero shot. That is a really key term here. Define that for us clearly.
It means the model works on a task it has never seen before, without any extra training. You take the model fresh out of the box, drop it into a noisy pub, or a lecture hall, or a car, and it just works. No fine-tuning required.
Okay, so to get a model that knows everything, they needed to teach it everything. And this brings us to the data. When I saw the number in the paper, I had to double check it. 680,000 hours.
It is a staggering amount of audio.
I actually did some back-of-the-napkin math on this. If you listen to this audio 24 hours a day without sleeping, it would take you roughly 77 years to get through it.
To put that scale in perspective, the standard academic datasets like LibriSpeech are usually 1,000 hours. Even the biggest ambitious projects before this, like SpeechDo, were maybe 5,000 hours. Whisper is over 100 times larger than that.
But here's the catch, and this is where the title weak supervision comes in. They didn't have 77 years of humans sitting there carefully typing out perfect transcripts, did they? That would cost a fortune.
No, that would be impossible. Instead, they scraped the internet. They found audio that already had transcripts associated with it. Think about podcasts that upload their show notes, or videos that have subtitles, or song lyrics paired with audio files.
But hold on. We all know internet subtitles can be questionable. They are full of typos, or they say music playing, or sometimes they're just totally out of sync.
That is exactly why it's called weak supervision. The labels, the transcripts are noisy. They are not perfect. In the old days, the dogma was that you needed perfect data to train a perfect model. Garbage in, garbage out.
That seems to be the golden rule of computing.
It was. But Whisper proves that if you have enough data, the scale outweighs the noise. If the model hears the word banana 10,000 times, and in 9,000 of those cases the transcript says banana, it learns the pattern. It effectively ignores the 1,000 times the transcript was just wrong.
So quantity really does have a quality all its own.
Ideally, yes,
Yeah.
but they did have to be a little clever about it. You can't just scrape everything blindly. They had to build filters to remove machine-generated captions.
Oh, right, because YouTube and other sites often auto-generate captions now using older AI models. You don't want to train your new AI on the mistakes of the old AI.
Exactly. That is a phenomenon called model collapse.
Yeah.
It's like making a photocopy of a photocopy. Eventually, the image just becomes a blur. So the researchers built heuristics to detect machine-generated text. They looked for transcripts that were all uppercase or had no punctuation or just looked robotic, and they tossed those out. They wanted human-generated text, even if it was weak human text.
So we have this mountain of 680,000 hours of noisy, messy human audio. How do they actually process it? I was expecting the paper to describe some revolutionary new brain structure, but they claim the architecture is actually pretty standard.
That is the beauty of it.
Hmm.
They didn't invent a new engine. They just put high-octane fuel in a standard engine. They used an encoder-decoder transformer. This is the exact same underlying architecture that powers GPT-4.
Okay, let's visualize this for the listener. I speak into the microphone, hello world. What physically happens to that sound inside the model?
First, the audio is sliced up. The model processes audio in 30-second chunks. It doesn't treat speech as a continuous stream. It treats it as a series of 30-second windows.
And it converts that sound into an image. The paper mentions log-mouse spectrograms.
Yes. Think of it like a visual fingerprint of the sound. Time is on the x-axis, frequency, which is how high or low the pitch is on the y-axis, and the brightness shows how loud it is. So the encoder part of the model looks at this picture. It scans the image of your voice, extracts the features. It says, okay, here are the foams, here's the tone, here's the silence.
And then the decoder turns that understanding back into text. But this is where I got a little confused, and I think this is where the real innovation is. The paper describes this system of multitask tokens. It sounds like the model isn't just writing words, it's writing instructions to itself.
That is absolutely my favorite part of the technical design, because they wanted one single model to do everything. Transcribe English, translate French, detect silence, timestamp the words. They had to give it a way to know what it was supposed to do with the audio.
So it's like a command line interface built right into the brain of the AI.
Exactly. Before it predicts a single word of the actual transcript, the model predicts a series of special tokens. It is like a preamble.
Walk us through that sequence. What does the preamble look like?
So a 30-second chunk of audio comes in. The decoder starts. First token, start of transcript. That tells the system, we are live. The next token it predicts is the language. So it listens to the audio features and predicts English or Korean or Swahili.
Wait, so it doesn't have a separate language detector piece of software running in the background? The model just figures it out as part of the sentence?
It is all one continuous prediction stream. That's the universal part. After the language, it predicts the task token. Either transcribe if you want it written in the same language, or translate if you want it in English. And finally, it predicts whether to use timestamps.
So the model is effectively saying to itself, okay, I'm starting. This sounds like German. I've been asked to translate this to English, and I need to mark the time for the subtitles.
Yes. And because these are just tokens, mechanically identical to the word cat or dog, the model learns to control its own behavior just by predicting the next symbol. This brings massive simplification. You don't need 5 different specialized models for language ID, voice activity detection, and translation. You just need one transformer that knows how to follow instructions.
That is incredibly elegant. It really simplifies the whole pipeline. But the big question is, does it work? We talked about the student failing the final exam. When they took this Whisper model, trained on the messy internet, and threw it into the zero-shot exam, what actually happened?
This is where the results get really provocative. On that famous LibriSpeech clean dataset, the audiobook one we mentioned, Whisper did not set a new record. In fact, specialized models that were trained only on LibriSpeech beat it. So on the easy test, the specialist wins. Right. If you study explicitly for the test, you will beat the student who studied general knowledge. But, and this is the big but, when they moved to other datasets, the tables turned completely. They tested on datasets with accents, background noise, technical jargon. The specialized models crashed. Their error rates doubled or even tripled.
And Whisper?
Whisper's performance stayed flat. It didn't care that the audio was noisy. It didn't care that the speaker had a heavy Scottish accent. It matched human-level robustness. It was the difference between a student who aced the quiz and a student who actually understands the subject.
There's one specific test in the paper that I thought really drove this home, the pub noise experiment. I just love that they actually call it that, essentially.
The EP043 dataset, yes. They literally took clear audio and digitally added pub noise chatter, clinking glasses, traffic, kitchen sounds at different volumes.
Measured in signal-to-noise ratio?
Right. So a high ratio means the voice is loud and the noise is quiet. A low ratio means the pub is getting rowdy.
And what did the graph look like?
As the noise got louder, the traditional models degraded almost instantly. It was a steep cliff. As soon as a glass clinked, the old models got confused. But Whisper held on. Even when the signal-to-noise ratio dropped below 10 decibels, which is a pretty loud environment where you'd have to raise your voice to be heard, Whisper was still transcribing effectively.
That validates the hypothesis perfectly. By training on messy internet audio, it had already heard a pub before. It wasn't confused by the clinking glass because it had heard clinking glasses in a YouTube video during training.
Exactly. It learned to separate the signal from the noise because it had to during training. It treats the noise as just another piece of context to ignore.
Now, we have to talk about how they grade these things, because the paper spends a significant amount of time complaining about the standard metric, WER or word error rate. I really got the sense the researchers were a bit salty about how their model was being graded.
Oh, they absolutely have a right to be. Word error rate is a very literal old-school metric. It compares the text the machine outputs to the human reference text, word for exact word.
So if the human typed, the cost is $10 million, spelling out the words, and the machine types $10, 000,000.
The computer grading the test marks that as a complete failure. It sees 10 spelled out versus the numbers and says mismatch 0 points, even though the meaning is identical.
That seems incredibly unfair for a model trained on the internet where people write things in a million different ways.
It is. Whisper, having read the whole internet, might prefer to write OK instead of OKAY, or it might use a timestamp format differently. So the researchers built a massive text normalizer. Before grading, they convert everything to a standard format. They expand contractions, spell out numbers, standardize dates.
And when they did that?
On some data sets, the error rate dropped by over 50%.
Wow, so half the errors weren't errors at all. They were just stylistic choices.
It highlights a growing problem in AI. As models get smarter and more flexible, our rigid, automated ways of testing them are becoming obsolete. We really need metrics that measure meaning, not just string matching.
Let's pivot to the multilingual aspect, because Whisper isn't just for English. It supports 96 languages.
117,000 hours of the training data was non-English. And the data revealed a very harsh truth about language learning in AI. It is all about volume.
The paper had a graph for this, a log-log plot.
It was a perfectly straight line. For every 16 times increase in training data, the error rate gets cut in half. So Spanish, which has tons of data on the internet, did great. But languages like Telugu or Khmer, which had very little data, performed poorly.
It's just a numbers game. If you don't have the hours, you don't get the accuracy. But there was one massive, glaring outlier in that graph. A complete mystery. The case of the Welsh translation.
Oh, the Welsh anomaly. This is a great lesson in data science. So when they looked at the translation task translating audio into English, Welsh appeared to have a massive amount of data, about 9,000 hours.
Which is huge. That's more than French. And I've been to Wales. I know people speak Welsh, but 9,000 hours of translated audio. That seemed highly suspicious.
And despite all that data, the performance was terrible. It had a BLEU score that's a translation metric of like 13. It should have been much higher with that much fuel.
So what was going on? Did the model just have a grudge against the Welsh language?
They dug into the dataset. It turns out the language identification system they used to curate the data had a bug. It was constantly misclassifying English audio as Welsh.
Wait, so the Welsh training data was actually just English?
Most of it, yes. So the model was being fed English audio, but it was told, this is Welsh, and here's the English translation.
So it was learning fake Welsh?
Basically, it was being gaslit. And because the input audio was English and the target text was English, it didn't learn to translate anything. It just learned to copy.
That is hilarious, but also a little scary. It shows that even with weak supervision, there is a limit. If the data is fundamentally lying to the model, scale doesn't fix it.
Exactly. There is a threshold where noise just becomes misinformation.
Speaking of misinformation, we need to talk about hallucinations. We are used to chatbots making stuff up, but I was really surprised to hear that a speech-to-text model can hallucinate. How does that happen? It's just supposed to repeat what it hears.
You would think so.
Mm-hmm.
But remember, Whisper is a predictive engine, not a tape recorder. It's predicting the next word based on patterns. One specific hallucination they found was the speaker name issue.
This is where it adds a name that wasn't spoken.
Right. Sometimes the transcript would say, Tim, I'm going to the store, even though no one ever said the word Tim.
Why? Is it hearing ghosts?
It is remembering the training data. It read millions of transcripts from TED Talks or news interviews. Those transcripts often start with the speaker's name. So if the audio sounds like a formal interview, the model thinks, oh, I know this pattern. I should put a name here. It's trying to be helpful, but it ends up hallucinating information it couldn't possibly know.
It's over-predicting context.
They actually had to do a round of fine-tuning on transcripts without speaker names just to suppress that habit.
There was another issue with long recordings. Since it only processes 30 seconds at a time, what happens if a sentence gets cut in half? Or if there is a long silence?
It can get stuck in a repetition loop. It transcribes a phrase, the window shifts, it sees similar features, and it transcribes the same phrase again. And he said, and he said, and he said. It's like a broken record.
So how do they break the loop? The paper mentions temperature fallback. That sounds like a sci-fi protocol. Core critical, initiate temperature fallback.
It's actually a brilliant failsafe. In AI, temperature controls creativity or randomness. A low temperature means always pick the most likely next word. A high temperature means take a risk, try something else.
So usually you want low temperature for transcription. You want accuracy, not creativity.
Correct. But when the model gets stuck, if the confidence scores drop, or if it detects it's repeating itself, Whisper automatically cranks up the temperature.
It effectively says, okay, my safe guess is obviously wrong. Let's get weird.
Exactly. It forces the model to explore different interpretations of the audio to break out of the loop. It is essentially automating the human process of, wait, that didn't make sense. Let me rethink what I just heard.
That is really clever. It's engineering a way around the model's blind spots.
It shows that raw model power isn't enough. You still need these heuristics and engineering tricks to make it usable in the real world.
So stepping back, we've got this massive model trained on the noisy internet that listens like a human. Why does this matter to the person listening to this deep dive right now? Why should you care about log-mel spectrograms and weak supervision?
I think the biggest takeaway is that good enough data at massive scale beats perfect data. This unlocks applications we couldn't do before. We are moving from a world where you have to speak like a robot to get your computer to understand you to a world where the computer understands you even if you're shouting over a blender.
It moves speech recognition from a feature that works sometimes to infrastructure that works always.
Real-time translation classes, automated meeting notes that actually get the technical terms right, accessibility tools for the deaf that work in a noisy restaurant. Whisper makes all of that viable. Passive listening, is effectively solved.
But the paper ends on a bit of a cliffhanger regarding English.
Yes, the saturation point.
They noticed that for English speech recognition, they were hitting diminishing returns.
Right. Adding more data wasn't dropping the error rate much further. They have squeezed almost all the juice out of the orange.
So we might be reaching the absolute limit of what a machine can do just by listening.
Which brings up a really profound question. Humans don't just passively listen. If I mumble and you don't hear me, what do?
I say what? Say that again?
You interact, you ask for clarification, you use context. The next leap in speech AI probably isn't better transcription. It is agency. It's an AI that knows when it's confused and asks, did you mean 10 million or $10?
That is the difference between a transcriber and an actual conversationalist. And until our apps start pausing to ask us what we meant, that is something for you to think about as we wrap up. That is all the time we have for today's deep dive into Whisper.
Thanks for having me.
We will see you on the next one.